I will be talking today about calculating the airspeed velocity of an unladen swallow. No, wait, I need a different presentation. This is a different kind of Python. Instead, I will be talking today about implementing strong data encryption in Python, a topic near and dear to my heart. I will save all of the shameless plugs for my current work. And to start with, I'll give a little bit of introduction about myself, so you can give hopefully a little bit of credibility to the topic I'll be talking about. First, a little bit about me. And the first thing I will open with is that it is currently 4 o'clock in the morning. I will hopefully get my caffeine intake up a couple slides in, but bear with me if my first couple words are a little bit slow. Other than that, from a professional standpoint, I've been in software engineering, mostly web and analytics for the last 20 years. Early on in my career, I was largely PHP and .NET based. The past 7 or 8 years has seen some Go, and my Python conversion happened, ironically enough, through a personal endeavor through Home Assistant. If any of you are not familiar with that, it is a home automation tool built in Python. And when you need to add things to it, or it doesn't recognize things like the inputs of your receiver, you need to write Python. And that was the first time I touched it. And here we are several years later, and Python is one of my main languages. I'm currently working at Ubiq Security. I think I mentioned Ubiq one other time in this presentation. This is not at all a sales pitch, but Ubiq is a cloud encryption company. So I'm happy to answer questions in depth about encryption or decryption, irrespective of the company at any point. And then most recently, I saw Batman, the movie. Those are also a picture of my kids at Legoland. I was maybe more excited than they were in the Lego pits, and I managed to watch the Batman Lego movie about 12 times over the course of 3 days while there as well. And the latest nerd exciting thing that happened to me is that I think for the first time in my career, I had an opportunity to use an X hours with git merge to clobber somebody else's changes, which was very exciting, and not something I get to do, and also something that forced me to go scramble to Stack Overflow to figure out how to do it when I needed to. So now on to our topics. Firstly, a little bit about encryption, and I'll give a little bit of an overview of what we're doing today. But the first section is really a primer to what encryption is, in case you're not familiar with it. And if this is not what you had in mind, or if you're already familiar with it, feel free to just kind of watch the pictures for this first section. We'll get into some more implementation details as we go. So what are we talking about throughout this? Well, obviously, we're talking about encryption. And we will talk about actual implementation details specific to Python toward the end. But to get there, I think it's really important to understand the context of data protection, specifically using encryption, but why you want to use it, why most of it is no good to use. There are lots of old algorithms. There are lots of ways to improperly use it, a lot of ways to use it that seemingly protect your data, but don't really. And then lastly, what you can do about that. How do you use it responsibly? How do you use it well? How do you use it in a way that will ultimately protect your data as much as possible? So first off, some definitions. Plain text. I'll use this throughout. Plain text is your message, the thing you're encrypting. Could be an image, could be text, could be lots of different things, but plain text. In my example, free pizza. Then ciphertext. Ciphertext is the encrypted version of your plain text. So in this example, if I did a simple character replacement of free pizza, I get this kind of nonsensical string, and that's what I refer to as my ciphertext. More definitions. Symmetric encryption. That is where you encrypt something, and the key that is used is known to both parties, both the encryptor and the decryptor. That is different from asymmetric encryption, which is where only one party knows each of the keys. Pretty much exclusively, I'll be talking about symmetric encryption in this presentation, but happy to chat about both at the face-to-face after. Now on to a little bit of history. If anybody recognizes this, I am old, but this is even before my time. Cryptography and encryption has been around for a long, long time. Thousands of years, in fact. Julius Caesar, back in his time, used basic substitution ciphers. That means you have an A, you replace it with a D, you have a B, you replace it with an E, something super simple like that, not dissimilar from a crackerjack decoder ring. But these kind of techniques have been used for millennia in terms of protecting data, especially in times of war or conflict when messages have been passed. Fast forward a couple thousand years, crackerjacks made this universally accessible to everybody, though it had been used exhaustively in World War I and would later in World War II as well. And then finally, NIST got its act together in 1973, though pushed largely because of IBM, and they came up with a standard by which to measure or to perform encryption. It was codenamed Lucifer. I can't tell you why, though it's probably in Wikipedia somewhere. But that was the first introduction of DES. Then about 25 years later, they sought out a new encryption algorithm, largely because DES is now crackable. I'll talk about why in a second, but they came up with AES. I believe the code name there is pronounced Rijnendel, but that was come up with in around 2000. So AES has been around for 22 years now. I suspect that as compute continues to grow and excel in our kind of modern technology landscape, you add something like quantum computing, or you just add something like the growth of processing speed, and we are not too far off from needing another algorithm that is continually hardened against brute force attacks. So a replacement cipher, my last definitional sort of slide. Caesar used this again, and it's called a monoalphabetic cipher. That means that each letter is replaced with another letter. His key was 3, same example, right? So this as a ciphertext became the best presentation ever. He probably rarely used that. I guess it was more about people and moves or cities or horses or whatever it is that Caesar talked about. But a simple replacement cipher, what that means is each letter gets replaced with another, you scramble it up. That's kind of weak. There are lots of other weak ciphers. That in particular was cracked through generally frequency analysis. It wasn't called that at the time, but it certainly was later in the 20th century, which means that to crack that cipher, to be able to decrypt it without the key or without knowing that replacement code, in his case 3, not very complicated, but to be able to crack that, those that were looking at the ciphertext did so by frequency analysis. That means they analyzed how frequently a cipher character appeared, or in what patterns it appeared, and correlated that to how frequently regular letters appeared. And by doing that, they could gradually start to identify what a cipher character translated to in its plain text and gradually decode the message. There are things other than just straight individual character frequency analysis, like double letters. In the English language, we get a lot of double T's, double D's, word endings like ing or est, things like that, as well as there's a kind of a phonic repeat sort of pattern within the English language, and there are corollaries for other languages where we see this repeat of letters that form a word in kind of a phonic or an alphabetic sort of way. So those sort of techniques were used to decode ciphers without having the key. And that same game continues today. Over the course of the past couple centuries, the cryptography advanced through monoalphabetic to polyalphabetic. That means that an individual character may correlate, or its ciphertext may correspond to multiple characters instead of just one, because it's using multiple alphabets to do this, and a kind of sampling of those throughout. And then homophonic, which is where a group of characters is encrypted directly, and then padded ciphers, which means that the key length is equal to the text length, which is actually pretty strong, but pretty impractical. And this game continues. In more modern times, it's not so much about the complexity of the number of alphabets you're using. It kind of is, but not in an intellectual sense. It's more about compute power. That DES was broken because a decryption kind of hack could be achieved by trying lots of different combinations. AES is just really complex, but the concept is almost the same between very modern cryptographic approaches like DES and AES to more historical ones like a simple replacement. The difference is the complexity of the math, and that the more modern ones are based on enormous alphabet sets because they're effectively numerically or binary based, and that allows them to work off many more than 26 characters. But we'll continue to see this cat and mouse. It is purely a processing or a compute power sort of equation as to why AES has not yet been broken. It's been 20 years, right? That's pretty good math, but we'll get there at some point. And so planning for the evolution of cryptographic changes, algorithmic changes, is important. So it's enough history. Now on to why do you want it? Why is encryption the answer? And ultimately, this thing we're after is protecting our data, and protecting our data in Python apps. I know so far much of this has not been Python based, but bear with me. But why do we want it? Well, firstly, OWASP says so. Take that with a grain of salt. We shouldn't just do things because we're told to, but OWASP generally well respected. And cryptographic failures in the latest kind of publication of OWASP got the #2 spot. It's influenced a lot by regulatory needs. GDPR, CCPA, those kind of things are increasingly focused on data privacy, and encryption is a really good way of achieving those. Data breaches, data hacks, data leakages, all of these things are much less serious if the data that leaks is just ciphertext, because then it doesn't expose anybody's personal information anymore. OWASP also talks about transport issues. I want to mention this just for completeness, but we won't really be focused on encryption in transit today. But OWASP has put a lot of importance on things like SSL and other transport issues. And then also OWASP reinforces that getting crypto right is hard. Algorithm choices, ensuring you do it at the right place, but keeping up with it is hard too. That imagine the changes that are necessary around all of the software applications that are currently using AES if AES becomes antiquated and crackable. Same thing that we had with DES pre-2000. Everywhere where that was used had to be changed. Now that's not so difficult if you're a one-person shop writing your own code. Huge deal though if you're a bank or a financial institution or a medical institution that has generally slow-moving processes and hundreds, if not thousands, of applications, each of which might have their own place or point at which they use an encryption algorithm. But also, forget about OWASP. If it's good enough for the Egyptians, it's probably good enough for us. Encryption as a mechanism has been used for thousands of years. Granted, we have improved a lot about that. And generally, sending something encrypted or a message and encrypting it is better than sending it in plain text, even if it's still Julius Caesar's replacement cipher. But modern encryption generally is pretty good, and we should probably use it. But also, encryption is a first line of defense. If you think about layered security as a concept, encrypting your data could either be viewed as the first or the last, but encrypting your data it should be used as a piece of an overall security protection mechanism for your data. It is not the only answer. There is a very good one, and generally is kind of accepted as something that's good to do. Though I won't try to convince you that it's the only thing you should do. Plus, it's kind of cool, right? This, it admittedly maybe gets told to you because your boss or InfoSec said so, and that's never fun. But you got to do what you got to do. But also, things like the matrix wouldn't exist without ciphertext, unless that's encoded, not encrypted, which is kind of maybe a fine line between them two, or maybe this is just Vim for those of us that don't use it. And it's nearly impossible to read or use, and I can never get out of it. So what's the problem with encryption? Why isn't it just generally used everywhere and solves the world's problems? Well, encryption isn't the problem. Encryption itself is not that challenging to use. It's where you use it. It's currently used at the storage layer almost ubiquitously. how it's used. Right now, if you're going to encrypt, you need keys. You might need an initialization vector. You get all these other pieces of metadata to use with your encryption, and like a database password, if you just throw those in your code repo, you might as well not bother protecting them at all. And then when encrypting everything everywhere is not always better, because there are implications to that, to things like searchability or data sharing or data aggregation. There are reasons not to encrypt because you want to use that data in a different way. But also encryption historically has come along with the notion of implicit trust, that just because I encrypted something, I'm good to go. But that's flawed in a number of ways, right? People need access to systems to do their jobs. And implicit trust means, well, I encrypted it, therefore it's fine. But implicit trust also means that if somebody can get to the system to do their job, they can also get to the data on that system. And that is not something I want to implicitly trust them to do. This is true with software engineers. We all have access to some code repository, and many of us probably have seen things in a code repo that shouldn't be there. Passwords, host names, example data. Maybe we need access to a production system to try to troubleshoot it. We get access to lots of stuff. DBAs get access to data. They don't need it to do their job necessarily, but if you're going to tune an index or create some schema, you naturally get access to the data on that database system. Again, an example of implicitly trusting somebody to data just because they have access to that system to do their job. Sysadmins, same thing. I can patch a box, therefore I can get to the data on that box. And even your cloud providers. Amazon can look at your data in S3 just because you have it in S3. If they need to help provide support to that bucket or something else, they can get to that data, and therefore they can expose it, or a hack to them can expose your data. And even hypervisors, right? Everything is virtualized at the system level and sometimes beyond. And your VM host can access the child hosts on it and give all of these kind of accessibility points to the data itself, because you're implicitly trusting these things that have system level access to the data beyond. None of that's any good. This is my angry cat. I don't actually have a cat, but I suspect it would look at me this way if I did. Used to have cats. Implicit trust is no good. And so implicit trust is not enough. What we need, if you have an incident, because that happens, it always does. This, for anybody that's missing the reference, is a picture from the office. These are disgruntled employees at their best. If you have an incident with implicit trust due to insider threats, an employee with admin access, a supply chain attack where your cloud provider or somebody else has a security breach, which gives those people access to your stuff, or just attackers, right? You have a breach because somebody stole admin credentials or used somebody's key card to get into your data center, whatever. All of these things are issues that are exacerbated because of implicit trust. If you have incidents from a people perspective, you also have issues because of application vulnerabilities. Forgive my like 90s movie quotes, but I started off on Monty Python, and I'm going to keep that theme running until I run out of movies. But application vulnerabilities, this, by the way, from Swordfish, probably the most unrealistic hacker movie ever made, but he's got lots of cool monitors. Anyway, application vulnerabilities, they exist too, despite us wishing they didn't. But access control, because your app is not secured enough in its own RBAC or whatever. Authentication issues, because somebody can get into your app. Maybe they brute force a password. Maybe you left an API unprotected. Or just general injection. Have you really closed all of your SQL injection issues? Have you really closed all of your cross-site scripting issues? All of these things lead to implicit trust issues, or make things worse because you've implicitly trusted to your data via system access. And this has happened in the real world lots of times. Big company had a security incident, compromised credentials, and they lost 500 million guest records. For anybody remembering, this was Marriott about 8 years ago. 500 million, that's a lot of people. Had that data been encrypted, nobody would have cared. Wasn't enough for these either. Application vulnerability, they had a SQL injection issue. and 130 million credit card numbers. This was the single largest credit card attack when combined with the Heartland and Hannaford kind of sister attack that happened. This was 7/11, but combined, this was in 2007, was the largest leak of credit card numbers in history because of SQL injection. Also, if those credit card numbers had been encrypted at the data level, it would have been an issue. And then my last example, picking on people, because smart people still mess up. I do believe that the people at Zoom were pretty smart. There was lots of press coverage over their security issues, but generally their issue was that they used ECB, which is a particular mode of encryption. They used it deterministic and with a single key, which means when they encrypted that penguin on the left, this is the Linux penguin, it looked like the one in the middle, which as a human, we can still recognize as a penguin. And so when you looked at your encrypted video or meeting recording, it was very viewable as its original form, when it should have been looking like the right, because they should not have used just a regular kind of block sort of cipher. They also did some bad things, like they generated the key in China and they said it was AES-256, it was really 128. But the point is, smart people still mess up encryption. It is complicated. There's a lot of moving parts. This was Zoom. But the one thing implicit trust does do is it checks the box and we get an angry kitty again. None of us want to just do what's right by the box. We want to do what's right by our data, by our customers, by feeling good about the software we built. So what's the answer? One more movie quote. I suppose this is a book quote, not a movie quote. I'll let you come back to that later. But the answer is encrypting data in a responsible way. Data in transit is a solved problem. It's very well accepted that it works. It's strong. SSL has been around forever. And it's kind of a solved problem, at least in a large way. I'm not going to talk about it here. But data at rest is still a big problem. There's usually a fairly long time gap between when data is encrypted, when it's stored on S3, on a database, on wherever, and then when it's decrypted. Could be minutes, could be hours, could be years. And also that same time gap between when it's signed and when it's verified. And so during that time, you have to manage things like keys. That makes it complicated. And those have to be protected, just like a password would. Data at rest also has key problems, right? Not just that you need them, but that key management is hard. There are all these key management services popping up because key management is hard. People try to make money on it. And nobody likes to lose keys because bad things happen when you lose keys. It's like losing the production password to your database. It's bad. Ask this guy, because he lost his keys. Admittedly, they were keys to a cold wallet or just the cold wallet itself, which you can't recover without it. And he's digging up a dump for the past 10 years. But bad things happen when you lose keys. You cannot recover them. If you can't recover your keys, your data is lost, much like this guy's hard drive. And data at rest has trust issues. We talked a lot about implicit trust, but the encryption mechanism that's used in most data at rest solutions and approaches is old. Even though the algorithm might be new, all of the kind of typical solutions that we all probably use, S3 encryption, Postgres encryption, all the stuff that operates at the data level is still implicitly trusting everybody that gets access to that storage system. And that doesn't work when most of the threats are aimed at your application, not the data. We've evolved over the years. Implicit trust isn't good enough anymore. 20 years ago, maybe it was. You had these guys. You had Iron Mountain. I was, unfortunately, admittedly, working in a place where we put a bunch of tapes in the back of Iron Mountain trucks and trusted them to get it to an offsite vault. Nobody does that anymore because beer trucks fall over. And data loss isn't about physical disks anymore. Private data centers they're gone. Largely nobody is using them. And nobody's stealing disks from a cloud provider anymore. And this dinosaur is sitting around drinking a beer because we don't need him, much like we don't need any of the empty data centers that big companies used to have. So he's happy that the beer truck fell over. And that happened plenty with Iron Mountain trucks, and you had disks all over the highway that people could then read. So 10 years ago, the general industry moved from storage level encryption at your servers to storage level encryption at your desktop. which is cool for all of the, beer drinking dinosaur and angry cat pictures I have on my laptop. But they didn't really think that physical disks is not the place where I'm at most risk. And not to mention, I'm not really storing sensitive data on my laptop or my desktop much anymore. Most of that is stored in the cloud or an application level. So finally, a couple of years ago, most of the cloud providers started to catch up, except the decades before them are still telling them that it's not about physical disks anymore. And as much as S3 encryption or cloud storage encryption or Postgres encryption sound great, and they do offer a level of protection against physical disk theft, they are still at-rest data encryption solutions that are the same as we saw 20 years ago, and they are not effective because, again, anybody that has access to your S3 bucket can read the data in it. Anybody that can run a query against your Postgres database can read the data in it, and that's a lot of people, ourselves included. As much as I hate to admit it, a software engineer shouldn't be able to read production data, even if I'm helping troubleshoot a production issue. And just by nature of giving me access to the system, they're giving me access to that data. So if encryption is the answer, but only when used responsibly, what is that? What's the real answer? And that is good encryption or responsible encryption or encryption used in the right place. And this is moving us in this evolution toward application level encryption or column level encryption, data level encryption. It's termed a lot of things. But what that is encryption where that's happening closer to the source of access to that data, where fewer people, fewer devices will see the plain text. So it is getting rid of that implicit trust model and limiting the amount of transparency there is to that decryption. What that means is, let me back up a sec. If somebody logs into your S3 bucket to view a file, that should not give them access to the data. If Amazon is helping you troubleshoot a data issue or just any issue on a bucket, or your sysadmin is configuring a new one, they shouldn't be able to read that data just because they got there. And so the fewer people that can see the plain text data, the better. And this term of transparent decryption, which is what everybody uses at the storage layer, right? Transparent disk encryption, right? Just decryption on access. Well, that's the whole point. We don't want to do that. We don't want to decrypt the data just because somebody opened the file. That's kind of defeats the purpose. We're going to decrypt the data because somebody had access to view the decrypted data, not just because they had access to get to the file. It allows for separation of data through controls of keys or even through your RBAC application control. And then lastly, it protects against a lot of these application level attacks too, because even if your data is exposed, ciphertext is all that exposure releases rather than plain text. Imagine Marriott's Thrill, if their 500 million records that were exposed didn't contain people's names or personal info, they just included a bunch of ciphertext that nobody could make sense of. That would have been a lot better. And then also it provides kind of defense in depth. Encryption, as I opened with, is a piece of a layered security approach. And encrypting your data provides a layer of security in the event that you have some kind of compromise of your cloud partner, your cloud host, your cloud service that you're hosting it in. And that's kind of a repeat of it. So it works at databases too, though it is different. Most of my examples so far have been for file type storage where the encryption is fairly straightforward. But databases too allows you to encrypt just the contents of specific columns if you're doing it at an app. If you're using Postgres's or SQL servers or MySQL's native encryption capabilities, you're encrypting the entire database. Effectively, you're encrypting the data file that represents that database. And any query is going to show you just regular plain text data. But what if only one of your columns has an SSN in it and the other 1,000 columns just have data that you don't care if anybody sees? Well, just encrypt that column. It's not necessary to encrypt everything. You can also then use separate keys to give granular level control to those individual columns. even if applications can access each column, if they don't have the key to decrypt it, they effectively don't have access to the data in it. Imagine this, you can limit what DBAs see. They still can retrieve the data in that column, but all they see is ciphertext because they don't have the key to decrypt it. And gasp again, you can let devs back into the database because it's safer. Not that we all get unfettered access to production, but our lives would be easier if we could access a production system when there is an issue, because there's no risk of us exposing or seeing data we shouldn't because it's just ciphertext. The bottom line being, don't just use database level encryption. It's not good enough. It exposes a huge amount of implicit trust issues that we don't want. So the pretty pictures, right? Summarize everything. You want to do it here. You want to do it at your app service, where you're not relying on storage layer encryption, where you're not implicitly trusting access to everything. You don't want to do it here. Whether that you replace database with file storage or any other storage provider, don't do it there, where everybody that can get access to the system can see the data, and where it's still susceptible to attacks and vulnerabilities. Okay, so how do I do it? Like, for real, how do I do it? Well, there are lots of solutions. I promise there's actual Python code. It's coming. But for databases, there's some hope. Most of the major providers have built-in encryption decryption functions. I'm not talking about they have, a encrypt my database checkbox, which is no better than a a full level disk encryption. But they actually have a built-in function at the database level that you can call to encrypt a particular string of data. And those can be used to facilitate your encryption decryption process at a column level. MySQL has it, SQL Server, Postgres, Snowflake, Oracle does. There's a bunch. MongoDB especially, and I have no affiliation with them, but they have done a great job of kind of pioneering this space of column level encryption decryption. They've added it at their driver level, which means that your app can control when and where to encrypt or decrypt as it's accessing the data. And unfortunately, it's only available for their kind of enterprise license, which I can't blame them for. But this is what I'm talking about. This leaves the data as ciphertext in the database. And if you access it by Navicat or some other SQL management studio or just command line, you just see ciphertext. But if you provide the keys during your ODBC call or whatever you're using from an app level, you can decrypt that data as it's transiting out of the database and into your app. And hopefully others are catching on. I would love to see that kind of capability that Mongo has across all of the database platforms. But database encryption gets complicated. I won't go into all the details, so I have one slide at the end, but think about how encoding, because ciphertext does not just give you, A through Z and 0 through 9. So encoding issues, field length issues. Ciphertext can be longer than your plain text. Or maybe you have an SSN that you're storing in just an integer column, and when you encrypt that, it's going to have alphanumeric. It's not going to work. Or even searchability, right? Once that data is ciphertext, it is challenging, if not impossible, to search. So database encryption has a whole lot of other kind of catches to go along with it. And there's some other niche solutions, API gateways, there's key management solutions, as well as vendors. Ubique Security is where I work. This is the only other place I'll mention it, but we offer a library and kind of SaaS API for doing that key management and encryption and decryption. There are others like us out there. One of them is Voltage. They do something very similar, except they're appliance-based, but there are lots of vendors entering the space that provide encryption management solutions as well as encryption and decryption solutions. And you can still roll your own. Finally, we are getting there. You just have to do all the hard work, which means that data gets encrypted and decrypted using application logic and application built-in functions into your language. This is the most flexible approach because it's agnostic to a vendor or technology. You don't care what cloud provider or what other subsystems you use. You're doing it all at the language level. And it's probably a good approach if you have kind of a multi-platform solution where you're deploying or accessing that same data from different applications written in different languages, and you need compatibility. This means also that you're not going to rely on storage level encryption, which is what we've been aiming at. And if you really want to kind of externalize the key management because you don't want to deal with that, you can do that, just that part with a vendor. But if you're going to do it yourself, do it responsibly. Always safety first. Which means don't use outdated or non-standard crypto algos. Don't write your own. Lots of people that are way smarter at math than I am have developed AES. It's there for your use. Don't try to write your own. It will be cracked. Also, treat your key material as passwords. They are the thing that allows people to get to your data. If you just put it in your repo, you might as well have not encrypted the data to begin with. Don't reuse your IVs. Initialization vectors control the randomness effectively of your cipher text. And if you use the same one every time, you're creating consistency across all the things that you encrypt rather than randomization. Also, in addition to using outdated crypto algorithms, don't use insecure encryption modes. Don't make Zoom's mistake, especially if you're encrypting an image or a video. And use the crypto-specific random generation that your language offers. If you're going to do it at the database level, just be aware of the issues or of the considerations to ensure that you have database compatibility. Ciphertext may be outside of the encoding. Ciphertext may be longer. It probably won't be searchable. And if people are accessing via a query, they're not going to see this stuff. Okay, let's do this in Python. I think I'm ready. Yes, we can. Napoleon Dynamite. Maybe not quite the same era as Monty Python, but equally as entertaining. Here's an example with Python. I've got some links, so I'm not exactly sure how to share them, but this is, I don't know, whatever, 30 lines of code. I will walk through it and then show it. So we only need a couple imports to do encryption and decryption in Python. There are built-in algorithm, mode, and cipher modules and methods for us to use. We only import OS so we can do a little randomization, which we may not do if we were being fed those things from outside. And we only need cipher algos and modes from the ciphers primitive. And then we bring in this default backend thing, though it theoretically is not needed after Python 3.1, though in my 3.6 example, I find it. So with those imports, I have some super secret text, which I'm encrypting. And then I have a key and an initialization vector that I'm going to feed into that encryption algorithm. My super secret text of the world needs more pizza will be what we encrypt and then see decrypt again. Once I have those three things are all I need to do my encryption. And I can start an encryptor. I can kind of instantiate my encryptor component. I can feed it the algorithm I want to use, right? Note there that I'm using AES, and my key size will dictate that it's 256. I'm using GCM as my mode. GCM is very strong. I'm also choosing these because I don't need to worry about padding. Some other algorithms or modes require that you pad out your plain text string to kind of an equal chunk of the block size. And then I'm feeding in the default backend. The default backend is not something you really need to worry about, though it does control kind of what cryptographic kind of approach Python uses in the backend. And then it's literally one method to create my ciphertext. I do an update of that secret text, and then I finalize, and I'm done. Ciphertext will now include the encrypted text of my plain text. Because I'm using AES and GCM, I also grab this tag, which is kind of a signature of that ciphertext. I'm going to need that when I go to decrypt my text, which I do here. So now I've got my set of things I used. I've got my key and my IV, and then I've got my tag, which came out of the encryption method. And again, my decryptor instantiation, very simple. I need to make sure I pass in the same algo and the same mode that I use to do the encryption work. And then I also just have a one method call to get my plain text. And that's it. I want to show that real quick in code. So here it is. Please no judgment of my use of VS Code. It's an old bad habit that I struggle to break. But generally, you can see this is the same. This is the same code, right? This is what we just looked at. That's it. That is all of 20 lines to do in Python. Super simple. All thanks to the inclusion of these crypto libraries that are built in. And then I'm just going to do some prints so you can see it. And if I jump over to here, you can see I just ran it because I never run it the first time in a demo. And this is all it does, right? Gives me my plain text, gives me my cipher text, and then I can see that my plain text matches. All right, now I got a couple other things in closing, and then we'll move on with our lives. So the last piece is like you can do it, and you can do it directly in the language. Python has a great set of facilities to do encryption, but when should you do it? Because you have now encryption happening at your app layer, which is good. That's what we want. We don't want to do it at the storage layer. You got to manage your keys and IDs. You have to manage your key rotation if you ever want that done. Good practice. If you prepared for algo changes, though these are probably once a decade sort of things, not every week. You have to worry about cross-app compatibility. The ciphertext of that is not going to match the same ciphertext with the same algo and mode if I do it in .NET or Go, unless I do some work to ensure it does. There are nuances cross language library that cross-language crypto library that control some of those things. And then you got to deal with all the database things. So to wrap up, encryption in Python, super easy. Right? What I have, less than 20 lines of code to encrypt and decrypt something. But doing it right takes more than just that. However, doing it right is our goal. Data protection is entirely about moving our reliance on disk or storage level encryption into kind of the time of the dinosaurs and get current. Do this at the app level so that you don't have an implicit trust risk that everybody that has access to your system, your database, your storage, your cloud environment, that all those people don't also get access to your data. But to do that well, you have to do encryption, decryption. You have to do it at the app level. You have to take care of your keys. Those are now your passwords. And you have to take care of your database ciphertext if you're doing it there. I think I am at time, but happy to talk more. I got to figure out how to jump over to the face-to-face room, but I will be there in a moment. And thanks everybody for your time.